This is the second of 4 short videos that will introduce you to the fundamentals of gas chromatography. There are 6 primary components of a GC system. Carrier gas. The carrier gas transports the sample from the inlet through the GC column, where it is separated into individual components. This can come from a pressurized cylinder or gas generator. The carrier gas type may be helium, hydrogen, nitrogen, or argon methane. The gas must be very pure, greater than 99.9995%. These high-purity gases can become contaminated between the tanks and the GC, so Agilent recommends installing a filter, for example, a gas clean filter, to ensure a clean gas supply to protect your instrument and column. Sample introduction. The most common method is to inject a small volume, typically around 1 microliter, of a solution into a heated inlet using a syringe. The requirement for GC samples is they must be able to be vaporized in order to be able to be carried through the GC column. Column. The column is the heart of the GC. A GC capillary column is a long, narrow tube that has a thin coating on the inside called a stationary phase. As the sample is transported through the column by the mobile phase, it will interact with the stationary phase and separate into the individual components of the sample mixture. The separation is based on the boiling point of each component and their relative affinity to the stationary phase. Oven. The column is temperature controlled in a heated GC oven. The oven can be operated at temperatures from near ambient, or lower with cryogenic cooling, up to 450 degrees centigrade, and can either be held at a constant temperature or can be programmed to change over time as required by the analysis. Detector. After the sample is separated by the column, it exits into one of many different types of detectors, where the amounts of the sample components are converted into electrical signals. Data system. A chromatography data system, for example, Agilent OpenLab CDS, is a computer software used to process the electrical signal produced by the detector into useful results, such as the identity and quantity of the sample components. Here are the key points to remember. Carrier gas from a pressurized cylinder or a gas generator transports the sample through a GC. A gas filter should be used to purify the carrier gas. A heated inlet is where the sample is injected onto the GC column. The column, in a temperature-controlled oven, is where interaction of the sample with the stationary phase inside the column enables separation of components. The detector responds to the components by generating a signal as each component elutes from the column into the detector. The chromatography data system is used to measure and identify the components and produces a chromatogram, a graphical representation of the separation of the components. The entire GC analysis cycle can be divided up into 5 steps. The first step is sample preparation, which is often the most time-consuming step, depending on the complexity of the sample matrix. An example of this step is extracting pesticides from fruit or soil. The second step, injection, involves rapid vaporization of a liquid sample, mixing with the carrier gas and introduction into the GC column. The analytes are then separated in the GC column in step 3 via a variety of physical and chemical separation mechanisms. After the separation of the analytes, the separated components are individually measured in a GC detector that converts some chemical or physical property into an electrical signal. In step 5, a chromatography data system, like OpenLab CDS, is used to process the digitized signal from the GC and use various mathematical equations to determine peak areas, peak heights, peak widths, and retention times. Here is a summary of the 5 steps. Steps 2 and 3 will be the focus of the next video. Step 1. The sample is prepared for analysis. Step 2. The sample is injected into the heated inlet. Step 3. Sample components separate from one another in the column. Step 4. As components pass through the detector generates a signal. Step 5. The time of elution, retention time, and the size of the peak are used to identify the components.